First of all, this question is basically a Unit 9 question. So, with vectors and stuff. So, the good news is, this material was cut from this year's AP test. So, don't give, like, once you see how you were supposed to do this, don't give this any more thought, for the time being. But I'm still assuming you want to at least get a quick rundown on how the parts B, C, and D at least were supposed to be done. So, but again, not something you're going to have to actually worry about going into this year's BC exam. But you said you figured out part A. Oh, geez, I can't believe I covered that up. It confused me there for a second. So you said you got part A correct, or you didn't have an issue with part A. Find the acceleration vector. So we have some unknown position vector, and then this would essentially make up your velocity vector. And so yeah, you would just have to take the derivative of these again to get like your components of an acceleration vector. So I took the derivative again, and I'm assuming so did you. Took the derivative again well, not again, I guess, but took the derivative of what was given here. And then whatever you get, if you plug in 2 radians, that is, this is what you get. And so that's the answer for the acceleration vector. Okay, now on to part B. I'm going to assume the only thing you were really missing here, or just weren't aware of, was the total distance of something, given like as a vector. It's essentially a formula. Okay, that's probably what you didn't know. Like, you would take the integral from wherever or whenever to whenever of a giant square root of the velocity x component squared plus the velocity like the y component of the velocity squared. And that's, again, it's essentially a formula, and this is the formula. So in our case, it boils down to, over the time interval, 1.8 to 2. So we're integrating from 1.8 to 2 of this, and you can just throw that in. Like, this was a calculator allowed, or required, I guess, a calculator required question or portion of the test. So you would just throw that into your calculator and get this. So total distance, just kind of a formula. Do I want to go into this any deeper? Square root, I mean, that's gonna get you the magnitude. No, I'm not going to get into that anymore for now. Part C. Find the x-coordinate of the position of the particle at time t equals 1. Alright, my first idea was to, they want position. So my plan A was, well, I'm just going to basically integrate this, because this is like the velocity component for x. So if I integrate that, I'm going to have a plus c, but then I can use the fact that, at time equals 2, our position for x was 5. So it's kind of like having an initial condition. So I had that written down to set up, like to integrate -1 plus e to the sine t. And I kind of hit a dead end actually doing the integration as like an indefinite integral. So I had a pretty good plan, but it kind of didn't really amount to anything. I kind of hit a brick wall actually integrating -1 plus e to the sine t. So the backup plan was to think about, well, what would be like the displacement? Like, what if I integrated from 1 to 2, and what was like the just the displacement of x? Okay, like from time equals 1 to time, because we actually know that at time equals 2 we're at 5. So here, integrating from 1 to 2 of the velocity sort of deal for x, and we figured out that the overall displacement for x was positive 1.605, just using our calculator. And so if we consider that our position at time 2 is 5, so we started at something and then we were displaced 1.605 to get to 5. And so we do 5 minus that to get back to like where we started at t equals 1, and we get 3.395. So hopefully that makes sense, doing this. And again, like, this would be just kind of like your displacement, okay? And part D talks about speed. Okay, again, this might be something that you are just not aware of yet. Speed has kind of a formula. Speed is kind of like the absolute value of the velocity. Okay, so it's called the magnitude, I believe, of the velocity. Anyway, it's essentially a formula. So and this maybe a little bit more inside scoop or whatever, but you might recognize this as basically like the length of a hypotenuse. So like it's the length of it's essentially the length of your velocity vector, like your velocity arrow. You know what I mean? And it's always positive. So anyway, again, there's essentially a formula for speed. Okay. Now, normally it's all of this. Okay, but here, since it's horizontal, like the path is horizontal at that time, we only really need to worry about the x component, okay, because it's perfectly horizontal. It's almost like there is no y component, okay, to anything, to the velocity, right? So here we can just kind of take the absolute value of the velocity for x. Okay, so whatever the velocity is as far as x is concerned, like the x component of the velocity, if we just take the absolute value of that, like that's going to be speed. So we only need to worry about x when it's going horizontal. And so when we plug in that crazy time value in for t, so -1 plus e to the sine of t, and again it's all absolute value, and so we end up with that as a speed. Okay, so that's the overall speed because of the absolute value. And then I guess it also says determine whether the particle is moving to the left or to the right at that time, give a reason. Well, the velocity as far as x goes was negative, so the velocity is negative. The speed's positive, but here it looks like the velocity was negative for x. And so that means it was moving to the left.